Okay, I just wanted to make this quick video to go over one more application from section 4.1 that tends to confuse students. And I know there's already videos for this in Alex, but I just wanted to make one really quickly so you could see it in Blackboard too really quickly. And the idea is we want to talk about what's called linear speed and angular speed and the differences between them. And as far as it goes, that's my attempt to draw a fan blade. But let's see. Suppose I have 2 points on this fan blade right here. Say this point and this point. If I want, I can then draw a line segment through them. And maybe I'll just draw a horizontal here so this we can see. And now I actually have an angle. And for both of these points, the angle I form with the horizontal is the same, theta. It's the same angle, obviously. Now, as far as linear speed and angular speed go, angular speed is just the change in the angle over the change in time. Which means, say, if I wanted to track how fast this blade goes as it goes from here to there, well, they're both going through the exact same angle theta because they both make the same angle theta. Which means their angular speed is going to be the same because they're going to both map out the same angle theta. So as far as the formula goes for angular speed, we can just say angular speed omega, that's not a W, it's actually a Greek letter omega, is equal to theta, the change in the angle, over the change in time. Linear speed is actually the regular speed that we're used to, change in position over change in time, the standard formula you've been using for a while now probably. But the interesting thing is, if you look at it right here, suppose I want to track how fast the linear speed is as the blade goes from here to here. Well, it'll take the same amount of time for both points. But this point actually has to go a further distance than this point. We can see the actual arc it forms right here. And this arc is bigger than this arc, which means if they both take the same amount of time, but this one goes a greater distance, well then this point actually has to be moving faster. So as it turns out, the angular speed of the 2 points is the same, but the linear speeds are actually different based off of where you are on the fan blade. As far as the formula goes for linear speed, well, we have our regular formula, V equals S over T, where S is just the distance traveled. But then, since we're talking about these arcs on this circular fan blade here, well, that S, the distance you travel, is just your arc length. So we can replace S with the formula for arc length. We said S was R theta, so that becomes R theta over T. But now, if you want to do a little bit of algebra, theta over T is just omega. Which means now, I can replace theta over T with omega, and I get R omega. And now I have a formula to calculate the angular speed and the linear speed. And again, just keep in mind, because this often confuses people, the angular speeds will be the same, because you move through the same angle in the same amount of time. The linear speeds will be different because where you are on the fan blade changes the distance you actually travel in a given amount of time. In order to kind of see this in action, I just wanted to run through one quick example so we can kind of work through a problem. So we'll say this. For our example, suppose a 2-foot fan blade moves at 90 RPMs. Find the linear and angular speed. Well, let's see. As far as it goes, we want to find both of them, but, well, at least in this case, given that the linear speed formula comes from the angular speed formula, then once I know the angular speed, I can just plug it in and multiply it by r, and I'll get my linear speed. So we're going to try to find the angular speed first. So let's see. For our angular speed, omega equals theta over t. Well, now let's see. The fan blade moves at 90 RPMs. Well, that means, let's see, my angle, the angle that I'm moving through, is essentially 90 circles. I'm not going to draw 90 circles, but it's going to spin like that. So I'm moving through 90 circles, so I guess theta is just 90 revolutions. And that's revolutions per minute, so my time is just per 1 minute. Now the only problem with that is, well, theta here has to be in radians, and 90 revolutions isn't in radians. So we just have to convert revolutions to radians and we'll be good. Let's see, we know from last time, each circle, it has an angle of 2 pi. So each revolution, it's a circle, has an angle of 2 pi. So there we go, we can convert. 1 revolution, I want to get rid of revolutions so they go on the bottom to cancel out, is equal to 2 pi radians. If I check my units, revolution cancels revolution. This answer is now in radians per minute, which will be my angular speed, angles per time unit. And now just do the math. Let's see, we don't need a calculator for this, we can leave the pi in there. 90 times 2, that's 180, and then the pi is there. So 180 pi radians per minute. And there we go, there's my angular speed. Now from there, we can calculate my linear speed. Linear speed v is equal to r times omega. Well, r is just the radius of the circle. It's a 2-foot fan blade, so r is just 2. Omega is just the angular speed I found, which is 180 pi radians per minute. And now that's easy enough to calculate out. 2 times 180, that's 360 pi radians per minute. If you want to get an estimate of what that actually is, throw it into your calculator, multiply it all out, and round your answer and you'll be fine. But there we go. Just using the formula, we can easily calculate angular speed and then use that to get linear speed. Just make sure to keep those straight in your head, which one you're talking about. If you want to test yourself a little bit, use this exact same problem, but pick a point halfway down the fan blade. So pick a point that is, say, 1 foot from the center. Solve the whole problem out again, and see what you get. We said when we started this, your angular speed should be the same. See if it is. We said, let's see, in terms of the fan blade, if you're on the edge, you'll be going faster than if you're closer to the center. So if we pick a point 1 foot from the center, I should be going slower, my linear speed. So run through the math, check it all out, and see if the angular speeds are the same, but if the linear speed you get is actually slower.